usually built on all the process nodes. So we started this research to know and to learn if we could also fault and attack chips built on more recent technologies. We focused on SOCs, which are deemed more complex, and more specifically on SOCs that are used in Android smartphones, in order to learn a bit more about the security of the ecosystem. So in the end, we settled on the MediaTek MT6878, which is fitting those criteria. So this chip, the commercial name of this chip is the MediaTek Dimensity 7300. It has been announced in 2024, and it's built on a 4nm process node, so quite recent technology here. It's also used in middle-end smartphone devices, just for you to know. So, what is a fault injection attack? So, a fault injection attack is a type of attack where we try to physically disturb the IC operation in order to induce architectural errors such as instruction skips, register corruption, or instruction corruption. And by leveraging these side effects, we can, for example, bypass security checks. So it really opens up new doors for attacks where there are no software bugs. There are multiple ways to inject faults. For this research, we picked EMFI, which is electromagnetic fault injection. How this works is by running a strong current in a coil above a chip, an electromagnetic field is generated, which hopefully disturbs the IC operation. The board that you can see on the right is called the Silicon Toaster. It's a board, it's an open source board, an open hardware board developed by our team that we use to inject fault using EMFI. So we picked that technique because it requires no PCB modification. You can just grab the phone, open it, and place the probe over the chip. So the boot sequence of MediaTek SOCs is quite complex. There are multiple steps before reaching Android, but for this research we only focused on the two first steps, which are running at the most privileged level, so which is EL3. When the SOC starts, it boots from the boot ROM, which resides in mass ROM. This stage basically initializes some peripherals, and then it loads the second stage, called the preloader, from an external flash into an internal SRAM, and it then verifies its authenticity and integrity before jumping to it. Well, we are not the first one to look into the security of MediaTek SOCs, and more specifically of the early boot stages. There is a great tool called MTK Client that gathers multiple vulnerabilities affecting MediaTek boot ROM. But this is not applicable here, as these vulnerabilities have been patched on recent SOCs. Also, there have been some research faulting MediaTek SOCs. There is NCC group that glitched the preloader signature verification in the boot ROM in order to load a tempered preloader. So they did that on a 28nm process node, so on a chip built with that technology. But it's far from today's technology, so we wanted to know whether it was possible today. The boot ROM binary is not available to us unless we have the capability to read the mask ROM or to somehow dump the ROM binary. However, we have access to the preloaded binary either by dumping the flash or by recovering the OTA update images. So we started by looking at it and doing some reverse engineering. So what the preload does is it configures various peripherals for the next boot stages, such as the DRAM, and it also loads the next stages from flash into memory and verifies their integrity. But there is one thing that is interesting in the preloader. It implements a so-called USBDL mode, which is a command handler mode. To enter that mode, you just have to perform a handshake on the USB, on the serial USB device that is exposed by the preloader. The handshake is just about sending the right bytes to this device. And among the commands exposed by the USBDL mode, the most interesting fault targets for us are the read and write commands, which allows to read and write from some dedicated areas, and also the sendDA and jumpDA commands. So DA here stands for download agent, which is a binary signed by MediaTek. So sendDA allows to load such a binary on the device, and jumpDA allows to execute it. We wanted to gain additional capabilities here at EL3, and ideally get code execution. So we started by looking at the write command. As you can see on the left, the USBDL protocol is a simple serial protocol. You start by sending the command ID, then you send the command argument, which here for the write command is the address and length. Then the handler performs the security check and returns the status. And if the status is successful, you can then send the data to be written. On the right, you can see a snippet of the decompiled code from Ghidra. The security check here is the region check with the address and length arguments. What is interesting to note here is that this code is not protected against single fault injection. If somehow we are able to corrupt UART to be 0 or to bypass the region check code, we are just able to write the data we want where we want. So the usual mitigation you find here is doing the region check multiple times and then comparing the result. So with that in mind, we decided to mount a fault injection setup. So you can see a picture of it on the left. The green board that is at the top is the silicon toaster that I showed you earlier. It's attached to a CNC in order to move the probe around above the chip. Then there is the SOC, which is just under the probe. And the SOC is resting on the red board, which is called the scaffold. It's also a board developed by our team, but more on that later. And we are using the blue board at the bottom, which is the Cintian. It's also an open source and open hardware board. It's based on an FPGA and is developed by Great Scott Gadgets. It's really a versatile tool to play with USB. You can emulate USB devices, use it as a USB protocol analyzer, or use it as a USB proxy in order to man in the middle the USB communication. But here for that setup, we use that board to get a trigger and reset. So as you can see on the left, the Cintian has 4 USB ports. The 2 ports that are on the right are directly connected to each other. So on the one end, we connected the SOC, and on the other hand, we connected the host, so we can communicate with the SOC. This connection is also connected to the Cintian. So the Cintian actually can see the USB communication. And by implementing a shift register, we are able to raise the GPIO to trigger a fault whenever specific bytes are matched. For instance, when the write command arguments are sent over USB. For a successful fault injection setup, we also need a reset in order to start from a fresh state before each fault. So luckily the Cintian has a feature that allows to enable or disable the USB power to the SOC. So by disabling and then enabling the USB power, we can implement a reset for the SOC. And we control that through the control port, on which we expose the USB device implemented on the Cintian. Everything did not go as expected. So first, the setup is not as straightforward as expected. For some reason, not all USB cables are equal. We had to play a bit with different combination of USB cables in order to make the setup work. But when that was done, the setup was only running for several hours, which is annoying because we want our fault injection setup to be running for several days. The issue here is that the USB host controller decided to die. So what the host controller sees when we are resetting the device is a USB device that is disconnecting, and then a new USB device that is connecting. And after a huge number of USB connection and disconnection, the host controller dies for some reason. We managed to restart it. However, not all of our tools support restarting without manual actions. For instance, our CNC stage, we need to define the base location when we start it. So to fix that, we tried using different computers we have in the lab. However, they all suffered from the same host controller problem. So after trying different solutions, we settled on the following solution. So we connected the SOC to a second computer. We still have the Cintian in the middle that is watching the USB communication and can provide a trigger. But this time, when the host controller of the second computer crashes, we can just restart this computer without affecting our other tools. So with that, our setup was running for several days, which is really cool. We observed perturbation, such as resets and errors, but no interesting faults. This was partly due to some jitter in the SOC response time. For some reason, when we send the right command arguments, the SOC takes a variable amount of time to answer. And this is not a jitter introduced by our setup. It also happens without the setup. And it does not seem to be a mitigation, as there is no code implementing it. So with that, we decided to take a step back and take a look at the boot ROM.
Right. So as Leo said, because of the difficulties of the USB setup, we decided to instead look at the boot ROM. The very nice thing about the boot ROM is that it actually implements a very similar command handler as the preloader does, but it is exposed also over UART, not only USB. And so that simplifies the setup a lot. We can actually zoom in, and we are only left with the scaffold board and the silicon toaster. So the scaffold board is really all we need for this work. It can be used for triggering, for interacting over UART, for powering up the device. In particular for power, we can use two external lab power supplies that can then be wired and switched on and off by the scaffold. And we can wire them to the USB and battery lines of the board that we have our SOC on. And so we can use either or both, depending on the board design at any given time. We also can solder wires to the UART, TX, and RX, test points or whatever, that we find on the board. They are quite simple to find, because both the boot ROM and the preloader emit quite a bit of logs over UART at boot time. So you can just bootloop the device, probe the points, and if you see something that looks like UART, it's the UART TX, and usually the UART RX is not far away from here. The only quite annoying point is that the boot ROM actually only goes into the command handler if it doesn't find the correct preloader to load into SRAM. So there's a few ways that you can try to corrupt the preloader. one of the easiest or at least most reliable one is to actually go and find the clock line running from the SOC to the flash, and from the scaffold you can then solder a wire and short it to ground whenever you need the preloader not to be read correctly by the bootrom, and then you fall into the command handler. So we used an approach to reduce such space, because for faults you can have a few relevant parameters, like the intensity and duration of the EM pulse you want to inject, the position of the probe above the SOC, and of course the timing at which you're going to try and inject the fault. Sometimes you can do a big search over the full space at once. Here we decided to first fix a position of the probe above the SOC, which gives us some perturbations, which is easy enough to do because, as I said, there are a lot of logs emitted over UART, so we can check if when we shoot with the silicon tosser, we get corrupted UART data back. And this way we can build a map of the different locations of the SOC package. And we found one where we have very, very reliable perturbations. And out of curiosity, you don't need to do that to inject the faults, but out of curiosity, we partially decapped the package of the chip, which you can see on the right. And actually the position of the probe that we found coincides with the two copperish pads that you can see in the package, which I don't know what they are exactly, but I guess some on-package capacitance or resistance or something like that. So probably the end physical effect that we are having here with the EM glitch is probably close to a voltage glitch, although I'm not sure exactly. Anyway, so we wanted to attack the preloader originally because, as Leo said, we had access to its binary, which is nice to try and find some attack paths. We do not have access to the bootrom binary, so we have to do some attack in black box. However, of course, there's a read command, just like in the preloader, and we decided as a first fault to try and fault the read command, to try to recover the bootrom text, and maybe that can give us more ideas for more severe attack later on. The only thing is we do not know where the bootrom is mapped to, but we can reasonably assume that it's mapped in 00, and so we can just try and read there and fault the check. Alright, so here we are trying to read hex 10 not bytes, words or half words. There's actually two different versions of the read command. You can read in increments of words or half words. Anyway, we can try to read that, and if you remember the protocol, the length that we asked for is echoed back to us. So that's what you see in the blue trace here, oscilloscope trace. It's the UART TX from the SOC. So it echoes the length back. And if we're trying to read in 0 but we're not injecting a fault, we get an error status back, which is hex 1D08, and then nothing. We do not get any data. One thing to note is that everything in this protocol is in big endian. Right, so at the byte level, the bytes are in big endian. So then we can assume that the security check is probably done somewhere before the error status is sent to us. And so we can try to inject the fault, and that's what you're going to see in the green line below. That's actually the pulse signals that is sent from the scaffold to the silicon tosser to inject an EM pulse. And so when we actually turn on the silicon tosser and do that, we get a few different, somewhat interesting behaviors. One of them is we just don't get a status back. So we don't know what the SOC does, but it doesn't look like it crashes because the UART line is still pulled up, but it doesn't answer. In the same time window, if we inject a fault, we sometimes also get only the first byte of the status, which is really interesting because, as I said, we hypothesize that the security checks are probably just before the sending of the status. So in this time region, we're probably close to where we want to fault. And so we concentrated on this window, and ran a lot of tests, and we were hoping to see a status hex 0000, which would have been a success, and then the data hex 10 half words sent back to us. We never got that result. However, we sometimes had a very interesting and weird behavior. We got what looks like an error status 1D00, and then a whole bunch of data, much more than what we asked for. And so this data is fully deterministic. It's not like random data. It's always the same. But we really didn't know what it was. So if you interpret the 1D00 as an error status and look at the data after that and interpret it in big endian, as you should in this protocol, then it really looks like absolutely nothing. And it actually took us quite a bit of time to realize that actually the 1D00 is not an error status. It's part of an instruction in Arch64 little endian. And we realized that the 1F20 O3D5s were nopes in Arch64. And as it turns out, we don't get a status, we just directly get a dump of Arch64 code in little endian. And it's actually the full ROM region starting from 0 that we get. It also includes, quite funnily, the SRAM region that the bootROM uses during execution. So really get a dump of the full snapshot of the full system state while we are executing the read command, including the stack. So, that's absolutely not the fault we were aiming for, but it's actually way better. So, yeah. And the fact that we could see the stack in the dump gave us an idea for an attack path. So the write command obviously doesn't let us write to SRAM, at least not anywhere. But if we manage to properly, this time, fault the relevant checks, we can attempt to override the stack and kick off a ROP chain on command return. So do basic software kind of stuff. You may think of stack canaries for that, but as it turns out, the command handlers are not using stack canaries. And this is not a linear overflow like you have in software. So actually we could just write past the stack canary. You don't even have to dump it or anything. So to do that, we just need the address at which we need to try and write to. So it's very easy, straightforward from the bootROM binary dump to actually understand what the stack layout looks like. So we can just find the snippet where the stack pointer is initialized. And then when you look at it, it's like there's a properly randomized cookie that you stored there. And then you just go through some function calls and you end up into the write command handler. And you find where its return address is stored at, and that's where we're going to try and write to. Okay, so let's look at the write command. Ignore the green line for the moment. Let's look at the blue trace. So we crafted a small payload, hex 4C in length. If we do not inject a fault, like if we turn off the silicon toaster, we get an error status back, 1D02. And we actually had quite a hard time finding successful faults, and we had to widen our such parameters, such space. And so one thing we did, which turned out to be successful, is we tried to inject more than one pulse. So we actually settled on 3 to 5 pulses, which we select at random, and we tried to inject that, and that actually gave us a success. So the success status is 0033 for the write command. And here you can see this is a real oscilloscope trace that I took from a successful run. And that you see that we can get the status back, and then we get to write our data wherever we want. And that's great, because now we have ROP, and we were able to confirm that we could do ROP. And that's extremely powerful already, ROP at EL3. However, we really wanted to do more interesting things with that. And so it would be very convenient to just be able to write code, compile it, and give it to the SOC to execute. So, of course, the stack is not mapped as executable, so we cannot just inject some shellcode and jump to it. However, with the help of some more software-inclined colleagues, Batista in particular, we realized that we could craft a small ROP chain that actually deactivates the MMU, and that makes the stack executable. I think it makes the whole memory just read-write execute. And this works out nicely too, because the bootrom operates with a one-to-one virtual to physical mapping anyway, so all the addresses stay the same when you deactivate the MMU. It's just like absolutely transparent. So that's great, and that gave us code execution. So let's try and see a demo video. Okay, so I have to explain a few things before I hit play. So you see the setup, you recognize the silicon toaster, the scaffold, and everything. The success rate of the fault is actually quite good. So we get a successful fault every few minutes, approximately. Here for this video, I selected a particularly lucky run. So it's only a few seconds long. And so you're going to see, we're going to boot loop the device, try to inject the fault. If it doesn't work, we just power down the device, boot loop it again, try to inject the fault. And so you'll see the LEDs of the scaffold blinking, and that's the boot loop. It's about 1 second long. Hopefully, if the sound works, you'll also hear nice clicks. This is actually the discharge of and the EM pulse going through the silicon toaster. And at some point, the LEDs will stop blinking, and that's when our fault has successfully passed. And then we inject a payload that just takes over the UART of the SOC and sends an arbitrary message back to us that the scaffold decodes and that we just print from Python in the terminal. Alright, I think I said everything, so let's go. And here we go. Just like that, we get code execution at EL3. Oh, it's looping now. Anyway. Alright. So, a few words in conclusion. So, of course, arbitrary code execution at EL3 is really powerful. In principle, it puts all user data at risk if system design roots confidentiality in the TE. Specifically on Android, it might enable an attacker to brute force the user's authentication secrets. It's not the case for phones that use an external secure element, which I believe in Android parlance basically means using Weaver instead of Gatekeeper and Keymints. As for the timeline, so we started this work in February. Spent a lot of time on the USB setup. Things accelerated quite a bit as soon as we switched to UART, which I think was a good call. We got the boot from dump in April. From that, it was quite fast to get to ROP, then code execution. And after that, we disclosed the issue to MediaTek, who informed all the affected smartphone vendors who use this particular SOC. And I must say that MediaTek's team was very responsive and quite constructive, so that's always very nice to see, so important to say. So a few insights that some of you may already believe in this, but it was quite new for us. Early in the boot chain, SOCs look a lot like microcontrollers. They may be built on advanced process nodes. They may run at higher frequencies, but they're not necessarily harder to inject faults into. And everything is single-threaded. It's really similar. We really loved in this attack bridging hardware and software. It's very satisfactory. I said it seems relatively unexplored. I don't know. Anyway, I might want to keep an eye for it in the future, because I think it makes for really nice attacks, and there may be great potential in it. And not using secure elements in embedded systems, i.e. chips not designed to resist these kinds of attacks, really puts user data at risk. And that's it for the talk. And if you have any questions, we'll be happy to take them.
Well, you already know the drill. So, do we have questions in the audience?
Very interesting talk. Thank you for it. In the boot ROM, when you reversed it, did you find any fault mitigation in the boot ROM, or was it just a plain code?
Actually, I don't think we saw any in the preloader, although I'm not sure. But in the boot ROM, there definitely is.
There were, yeah.
Just not enough. Yeah.
Okay, thank you.
Any other questions? I noticed that, again, it's the second time that in these 2 days that EM injections were used. And they also realized in the previous talk yesterday, that the glitch was very similar to what voltage injection would look like. Did you consider using voltage glitching, or like why you didn't do that?
We shortly considered it. The problem is if you want to do voltage glitching, you basically have to understand like the different power rails elementing the SOC. You have to understand power sequencing maybe to boot it up properly. And so that's a lot of reverse engineering work that's just not needed if you use EMFI. So that's just way easier.
All right. Any other questions? Yes.
Cheers, guys. I was wondering how you went about instrumenting scaffold for the Dimensity SOC itself. Did you end up kind of taking a phone board with the 7300 on it, or did you end up actually kind of spinning your own kind of target board for scaffold?
Yeah, no, we didn't spin a board. So I actually put up the picture maybe. It's a smartphone board. We just took a smartphone that used this chip. We opened it, extracted the main PCB, and then we just soldered onto a scaffold daughter board which has nothing on it. But then it just lets, maybe you can see the small wires. We can just solder some small wires to test points or pads on the PCB, and yeah.
Do you plan to release the ROM?
No.
Worth asking. All right. Let's give another round of applause to Charles and Leo.